All right. Hey, everyone. Welcome to the cloud computing tutorial. I understand it's been already a day chock full of tutorials, so I'm hoping this one can be kind of fun and interactive as well. So I'm going to be monitoring, I guess, the tutorial prompts Slack channel for any additional questions or responses to the questions, but I'll go ahead and get started by sharing my screen. And so now I believe you guys can see the cloud computing tutorial.
Yeah, we can see that.
Okay, cool. So yeah, I'm going to be talking a little bit about cloud computing today. We've already seen a lot about data access and ICESat-2 data, so we're going to focus a little bit more on, sort of like what is the cloud, what is the difference between data locally or on-premise at a DAC or on the cloud on AWS. So first of all, who am I? My name's Aimee Barciauskas. I'm a data engineer at Development Seed. Development Seed is a company, and mostly I work with NASA on putting their Earth observation data on the cloud. So have some experience working with ICESat-2 data, specifically the ATL08 data set, and moving that to the cloud to support specifically biomass, above ground biomass estimation. So that's just a little bit about me. I want to say thanks to so many people for helping with this tutorial, specifically Michaela, Jessica, and Scott for their help. Echo the thanks to Luis Lopez for the work on the NSIDC Earth Data Library and the demo notebooks, as well as contributors to the Dask tutorials. So I'll be going a little bit over Dask in this tutorial. So those tutorials, some of the content that I'll be going through was taken from those Dask tutorials. So I just linked to the contributors there. So first, I just wanted to get started with some icebreaker questions. So is everyone who wants to be logged into this Jupyter Hub and have their notebook open, or does anybody need more time? And I guess people can say that they need more time either in the tutorial prompts, things that we're using the chat, right?
That's right.
So I'm going to, while people are getting set up still, I'm going to put this first question into the tutorial prompts, which is, when you hear the term cloud computing, what's the first thing that comes to mind? And then the second prompt is, so hopefully these gets the wheels turning after lunch. So if you can take a few minutes to respond to those, I'm interested to hear also what concepts or tools are you hoping to learn more about in this tutorial, even if we don't get to them. I think it will help inform future tutorials. Remote storage, so people hear cloud computing, they think of remote storage, big data, not having to move data around, scalability, Amazon, fast, Google Earth Engine, SBatch. What's SBatch? I don't know SBatch. Is that related to my PC is happy? Data centers. Okay, cool. Yeah, and then as we move forward, if you get a chance to not having to download data, very true. What concepts or tools are you hoping to learn more about in this tutorial? Feel free to add to that prompt also as we move forward. Like I said, I'm interested to know, even if we can't tailor this tutorial as is, to tailor future tutorials on cloud computing. Okay, so the learning objectives for this tutorial, oh great, we have Tasha, Dask parallel computing. The learning objectives for this tutorial are to get a little bit of the primer on the difference between code running on your local machine versus a remote environment. The difference between data hosted on cloud providers like AWS and on-prem data centers. I know some of that was covered during the data access tutorials, so I'm gonna just revisit that material briefly and the difference between how to access data hosted by NASA DACS on-prem and then the cloud versus cloud/S3. So when I say the cloud, usually in this context, we're talking about NASA data. So that's NASA's Earth data holdings on AWS S3, which stands for Simple Storage Service. And then we are going to also talk about cloud computing tools, specifically a framework called Dask, which Tasha mentioned earlier. So key takeaways, I'd really just like, you guys are already like digesting a lot of information and trying to do a lot of work this week. So I think if I can give you just like at least one tutorial or tool to try in the future, that would be great. So the sections are going to be talking about local versus remote compute resources, data on the cloud versus on-premise, how to access NASA data, and tools for cloud computing with a brief introduction to Dask. So each section is going to include some key learning points and at least one exercise. I want to make sure that you have time now to configure your screens so you can see both the tutorial and both the tutorial screen and your own Jupyter Hub to follow along. It will make one of these things a little bit easier if we are also logged into Earth data. So I'm already logged in, so you can take a moment to log in there as we use Earth data search. It will be helpful if you're already logged in, and you'll see why in a few minutes. Okay, cool. So local versus remote resources. So question for the group, what is the difference between code running? What is the difference between code running on your local machine versus this remote Jupyter Hub? So as you're probably aware, this code is actually running on a machine somewhere in AWS land. So while we're running this browser, I'm running a Google Chrome browser on my laptop. This Jupyter notebook is actually running on presumably an AWS EC2 instance somewhere in one of these AWS data centers, which are located mysteriously around the globe. So what type of resources are, let me see what people said. Jessica says, I don't hear my computer fans whirring. Yeah, so hopefully if you're running really compute intensive things in this notebook, it wouldn't actually cause your machine to go crazy. However, it would, if you're making really crazy visualizations, that would require probably your own graphic processing unit. So it could still happen. Yeah, okay, so there's a few commands to run here that basically just show us how many CPUs are available on this machine that we're on and how much memory is available. So first exercise is, how many CPUs does your machine have? How does that compare? So I'm curious, actually, if people have a moment to, if you're a Mac user, you can open up a terminal. If you're a Mac user, you can open up a terminal and copy and paste this command to get how much, and let me see if I can probably do that real quick too. So I just opened up a terminal, and if I copy and paste that, I can see how many CPUs. So I have 12 CPUs here, physical CPUs. I have 6 CPUs. So I'll give people a minute to do that if they can. There's also some instructions for how to do that if you're running Linux or Windows. Let's see, 8, cool. Okay, so now what's interesting, right, is mine has 6, and this machine that I'm running on actually just has 4 CPUs. So, and I see pretty much everybody has, yeah, more than 4 in the chat. So when might you want to use a remote machine, and when might you want to use your local machine, and why? Julio says 2, I win, so maybe. Remote when you need more CPUs than local has. Yes, that's true. We could have gotten a bigger machine than we're currently running on. Depends on the task. For instance, you might want a GPU, which is a stronger, yeah, for ML, you might want to use a GPU, which is a stronger processing unit. To extract data from big data sets when you still want to do other things. Yeah, I like that one, when you still want to do other things while your tasks are running. So one really good reason to use a remote machine is like you don't want to have to leave your laptop running all the time, right? You want to like go out for a drink after this, but you still want to be able to process data. So, you know, one of the nice things about being a cloud engineer is your computers off in cloud land can go work for you while you go do other things. Of course, you have to be careful to make sure that you shut them down as well, because that's the other danger is you leave things running for too long and you forget to shut them down and you cost whoever a lot of money, and that's not good either. So you have to be careful. Cool. Any other thoughts on remote versus local? The other thing I'll mention, obviously, is when you're using a remote machine to run your code, you can use that remote machine, right, to connect to lots of other nodes in the same cloud environment, right? And they will have, so just having access to this machine, even though it's not as maybe as powerful as your local machine, it's co-located with all of AWS's, you know, server farms, right? So it's going to be able to actually access, and we'll talk a little bit about like Dask gateway clusters, but basically Dask clusters could be located on many machines. It could be local, but you could have a cluster of machines that's located in AWS or in Google Cloud or Microsoft, any of the cloud providers. And even though the code that you're writing might be on a small machine, it might be able to send work to all those other machines. Cool. So that's why it's important to understand data on the cloud versus on-premise and how to optimize your workflows for getting data co-located with compute. So I know that a version of this diagram was shown previously, but basically wanted to highlight how all of NASA's DACs, the Distributed Active Archive Centers, so they have these data centers that they've been using traditionally to house all the data, and they each have their own science domain, which is another cool way to look at it. So they're still tasked with the goal of basically maintaining and curating all of their, you know, domain specific data sets. However, instead of storing those data sets locally on-prem, they're migrating a lot of those data sets to AWS's Earth Data Cloud. NASA's Earth Data Cloud, which happens to be on AWS Simple Storage Service. So at this time, most data sets are still located and accessible on-premise. However, it's a very high priority for NASA to move all of these data sets to the cloud, as you guys have, as we've already been talking about. And so the things to be aware of is, while these data sets are still distributed, the DACs are in the process of moving them, and the services will be co-located in the cloud with that data to make the performance optimal and also to be cost optimal. Because when the services are co-located with the data, we don't incur what we might call egress costs. So cost to transfer the data out of AWS onto your local machine or onto an HPC system, when we can co-locate our compute resources, so our EC2 instances, our elastic compute instances, when we can have those resources, that code running in the same AWS region as the data is located, then we don't pay any of those oftentimes very expensive egress costs. So users are encouraged to access the data co-located in the cloud through AWS computer services like this Jupyter Hub. So exercise, so navigate to search.earth data.nasa.gov and answer what I hope are some sort of easier questions. But let's see. So when you navigate to search.earthdata.nasa.gov, oops, which DAC, you might be able to answer this already, but which DAC hosts the ICESat-2 data sets? And so I guess you win if you answer it the fastest. And then second question, which ICESat-2 data sets are hosted on the AWS cloud? And how can you tell using Earth Data Search Client? Michaela says, I know. So I'm going to do this myself. So if I go to search.earthdata.nasa.gov, and if I search for ICESat-2, I'm going to see some data sets. How do I know which are available from AWS Cloud? So I'll just go ahead and answer this question. Okay, so we have one response from Tasha. Yes, so if you click the available from AWS Cloud dataset, and I'm not going to see anything right now because, as we all know, that the secret here is to put in SIDC CPRD, I think. And let's unclick this. I should get it. I'm probably spelling something wrong. Or it's supposed to be capitalized.
You just need to be logged in, it looks like. I don't see your name over in the top right.
I was already logged in. Okay, interesting. Maybe I just need to re-log in to Earth Data. Thank you. All right, so now these should show up. Cool. So let's go back to our regularly scheduled programming. Okay, so what did we learn? So NASA has a new cloud paradigm, which includes data storage. It includes data stored both on-premise as well as on the cloud. I really like this diagram from PODAC, where you can see there's still data storage on-prem as well as in the cloud, and we're locating. The important part, is that we're working to co-locate all the tools and services with that data storage. So final thought, other cloud providers, there's the Google Earth Engine data catalog, as well as the Microsoft Planetary Computer data catalog. So those are good resources for additional data sets. Not all data is located on AWS. AWS also has its public data registry, open data on AWS, and its sustainability data initiative. So there's lots of open data out there in addition to NASA's archives. Okay, so how to access NASA data. So I know we've gone over this in previous tutorials about data access. So I do want to highlight this one exercise though. So NASA uses Earth Data Login to authenticate users in general to track usage, right? So you must apply EDL credentials at some point in some part of your workflow to access. They need to know who you are to track access to that data. And so while it's publicly available, you do have to log in at some point. So you can access data from NASA using these NetRSC files locally, which store your EDL credentials. And there's a really great NASA OpenScapes tutorial authentication for NASA Earth Data, which offers an excellent quick tutorial on how to create a NetRSC file and use it. The exercise is to review the tutorial, or as I think some of the other tutorials as well use this strategy. And why might you want to be careful running this code in a remote shared Jupyter Hub environment? Great. Yeah, so it's going to save the password, it's going to save your credentials into a file that's stored on this remote machine that other people have access to. So you have to be careful. You know, it's not always easily accessible to other users of that machine, but if other people are able to log into this machine, and just the fact that it's a cloud instance, right? It's an EC2 instance, and you know, one of the things that we've been facing recently is the possibility of you know, more increased Russian hacking. So it's just something to be careful about how you handle your credentials in a cloud environment. So this is kind of a PSA about that. Okay, so exercise 2. So this is using Earth Data Library to access ICESat-2 data, quote unquote, on premise at NICDC. So these are some really nice diagrams about programmatic access, I believe, that are from the Earth Data demo. And so this is basically demonstrating, this first diagram is demonstrating how this works when you're purely working with your local machine, your laptop, where you're going to download the files to your local disk and run some code on your local machine. Versus the alternative where you want to process in the cloud, right? So this is the paradigm that we want to move to, where there's this cloud region. So for example, like an AWS S3 US East 1 cloud region. And there's an object store, which is basically synonymous with simple storage service, or S3, where there's a bunch of objects, which is the same term as a file in our case. And then you have your compute cluster. So that's like a Dask compute cluster, for example, that has workers and scheduler, and that's hooked up to a notebook. And you can see how like there might be one object that you've loaded into the notebook, but a lot of them are being handled by the workers. And then the output is the figures. So we can go through this code pretty quickly, basically demonstrating how to use I already have a netrc file actually, I think here, that I've created previously, it must be. So I'm already authenticated. And so let's see if I remove let's just demonstrate this. Now this should use the interactive. Okay. So now I'm going to be using a session, which is the key here. We have a session in memory and not using our netrc files. And so then I can load in those granules and I can check if they're cloud hosted. So this is using the HTTP, the NSIDC on-prem data storage, and I can download those files and I can open them. Okay, so question now is, which NSIDC data access paradigm does this code fall into? So is that 1 or 2, or is this a search, download, process, research, or search and process in the cloud? So is this processing sort of in your local machine, or is it processing in the cloud? Nice. All right. I think Lawrence might take this one. So it's kind of a combination, because the objects themselves are still on-prem at NSIDC. However, we're loading them into a notebook, which is in this AWS cloud region. So it's actually a combination. It's a little bit of a trick question. Okay, so then the one other thing I wanted to demonstrate, this little trick that I'm not sure if other people got a chance to check this out with Earth Data Search, but hopefully it will be a useful reminder. So there is a pretty nice way to do programmatic access. So, okay, so we're going to access cloud optimized GeoTIFF from S3 using Earth Data Search. And there's a bunch of good tutorials, again, from the NASA Oceanscapes initiative on how to do this. But essentially, on different ways, all the different ways of accessing cloud optimized GeoTIFFs and NetCDF. So I definitely encourage you guys to look at the different options. But essentially, what I wanted to demonstrate is that we can use this programmatic access, right? So we have this requests.get S3 credentials endpoint from different providers. So these are the S3 credentials endpoints. So we can do this programmatically with requests. Another cool trick that I learned about recently, so I'm going to do this example with HLS data, is if you load up something from AWS that is available through AWS Cloud, and you click this little download icon, you get the download files option. You also get AWS S3 access, and you can click get AWS S3 credentials, and you can see it's going to the same endpoint to get those credentials. So you can also do it that way. And you can add the credentials here. Again, not wanting to commit this, but these are also temporary credentials. They expire in, it looks like, later today. And so, yeah, so basically just was able to add those credentials here, and open that file with read or X-ray because it is a cloud optimized GeoTIFF. Cool. So what did we learn? How to use Earth Data Library to access data sets, and how to use Earth Data Search to generate credentials. So question for the group. When making a request to Earth Data files, how do we know if the data are coming from Earth Data Cloud or on-premise? So the answer is you can usually tell because the file URLs themselves will either have, you'll either be using the S3 link, or if we go to if we go to, let's see, I need to copy this link address and inspect it. You'll see here that this domain is the same as the S3 credentials endpoint versus NSIDC, which has this pretty obvious on-prem like DAC. The DAC has its own web server, right, that it's using to serve these data sets. So that's the domain that's here versus a domain like for this HLS data set where the domain itself maps to the same domain as the S3 credentials endpoint. Okie dokie. So we've spent a lot of time on how to access the data because that's the first step to taking advantage of cloud compute resources. Once you have developed a way to access the data on the cloud or on premise, you may be ready to take the next step and scale your workload using a tool like Dask. So Dask is just one framework, but it's a very popular framework in the geospatial sciences community for handling multi-dimensional array type of data like you guys have been working with in the past. And so Dask has become a really popular tool. Probably many of you may have heard of a ecosystem of tools often called Pangeo, that and how Pangeo has sort of fostered an ecosystem of tools for doing large scale compute with geospatial data. So Dask is a flexible library for parallel computing in Python. So it has two parts: dynamic task scheduling, optimized for computation. So there are many types of Dask collections. There's Dask arrays, is very similar to NumPy arrays. Dask data frames, very similar to Pandas data frame, based off of Pandas data frame. Dask bags are like Python objects or JSON objects. So that's for more sort of arbitrary types of collections. Types of data can even be used for things like parsing log files for analysis. And then there's other types of collections like Dask delayed and futures, which more have to deal with how and when you're processing your collection. So futures are usually computed right away, whereas Dask delayed object collections are only computed when you call compute explicitly. So those collections are organized into a task graph, and we'll see what that looks like. And then they're sent to schedulers to actually execute either on a single machine or on a distributed cluster. So for this exercise, we're just going to go through a very simple intro to Dask to understand some of these concepts. So I'm going to start a local cluster with 4 workers, and I can sort of inspect what that cluster looks like by calling client and then cluster info. You see, we have a local cluster with 4 threads and 15 gigs of memory. And we can also actually see, that there's 4 workers here and how much memory each worker is taking up 1 thread with with a little under 4 gigs of memory. So let's send some work to our local cluster. So I'm going to define 2 functions here, one which increments its argument and one which increments by 1 its argument, and one which adds 2 arguments together. And to sort of demonstrate the time spent in one process versus in multiple processes, we're calling a sleep function as part of these 2 functions. So without the Dask cluster getting involved at all, I'm going to call this, and I'm going to use the time magics to calculate how much time it took to run this increment, and then add these 2 values, and we get the answer 5, which I believe to be the correct computation, and a total time of 3 seconds. So now we can use the Dask delayed decorator to use our Dask cluster to do this, to do the same computation. So I'm going to pass the same functions that I defined earlier here. I'm going to pass those as arguments to the Dask delayed decorator. And so this computes automatically because I haven't actually called compute yet. I've just defined my task graph. I haven't actually scheduled the work yet. So yeah, so nothing's really happened. I've just defined some Dask delayed objects. So we can even see if we look at what Z is, it's a delayed object. And so when I call compute, then we get the same response, but it happened a little bit faster, right? We got the answer 5, but we got it in 2.2 seconds as opposed to 3 seconds. So we can visually look at what just happened, where basically this is a way to visualize the Dask task graph. So we had 2 increment functions, which were basically being called in parallel, and then an add function, which summed the results of those 2 increment functions. So some questions to consider. So why did we go? I'll put this in the prompts as well. Why did we go from 3 seconds to 2 seconds? Why weren't we able to parallelize down to 1 second? there is some overhead. I think that in addition to some overhead, like Jessica said, some computations relied on others. So we first had to run increment. So assuming that increment happened in parallel, but took 1 second, add also had to occur and take 1 second. So both of those are true. And yeah, Felix asked a good question about using the multi-process library for multitasking. Is there a big difference? And my understanding would that the biggest difference would be that Dask, you would be able to more accurately control how your data is being chunked over the processes and also send to other machines. But yeah, so I'd be interested to read that Stack Overflow article as well that was linked there. All right, cool. So we just used local threads here to parallelize this option. So what are some other options for running our code? So I'm also going to demonstrate, how to both scale your cluster and also how to scale your cluster and also how to basically some other options for running your cluster on remote instances. So there's something called Dask Gateway, which provides a way to connect to more than one machine running using Dask workers. And I'm going to demonstrate that in a second. But what we're going to do, since we have the time, is we're going to go a bit through the Dask tutorial and the Pangeo tutorial gallery. So the Pangeo project, like I mentioned earlier, is a really great ecosystem of both people and softwares for doing large-scale geospatial science work. And there is a really great gallery demonstrating how to do how to basically use Dask and X-ray and all these tools that we've already been talking about in real science use cases. So the one that I'm going to do a little bit of a preview of is this Pangeo tutorial gallery, which has, sorry, this thing is getting in my way. This Pangeo tutorial gallery, which has a Dask tutorial intro. So I might have to restart this quickly, but it should be fresh. So let me just start this binder hub again. And this is this should be something that you guys can also run yourselves if you navigate again to this gallery.pangeo.io. I wouldn't recommend doing it all at once, but there's this Pangeo and Dask Gateway tutorial. I'm going to the Pangeo tutorial gallery and launching a binder, and once it launches, we can go through that. So the other thing that I was going to demonstrate is using a Dask gateway to scale your cluster. So there's different options for launching a Dask cluster. There's a DIY option, which is using QHub, which is an open source set of tools for running and maintaining your own Jupyter Hub and Dask Gateway environments. So this loaded up. So I'll demonstrate about how to use something like QHub to use Dask Gateway in a second. But first, I just wanted to do a little preview of these tutorials using the Pangeo Jupyter Hub. So like we said already, it's a parallel computing library for analytic computing and provides dynamic parallel task scheduling for things like arrays and data frames. So we've already loaded up a local cluster. In this, I wanted to also demonstrate how to scale your cluster. So I'm going to actually sort of combine the things that we were learning about earlier in terms of, okay, well, I'm going to use a local machine, but how much how much can I actually use? What's available to me? So I'm going to go back to, I'm sorry for all the scrolling, and I'm going to check out how many CPUs does this machine have. So this machine has 8 CPUs, and how much memory does it have? It has 51 gigs total memory. So now I know like what's available to me in terms of scaling up my local cluster. And so first of all, I can always use something like cluster.scale to check out how to do this, and it will tell me I can scale n. It can scale n, where n is the number of workers, and it can also scale, you can tell how much memory to give each worker and how many cores to use. So I'm just going to say cluster.scale, and let's say I'm going to say 4 workers, and memory, I'll say I'll give each worker 4 gigs of memory. So now if I load the client, I should be able to see what's changed. So now I have 4 workers, and I believe, yeah, and I should be using more memory than previously. So I'm going to actually go through a little bit more of a science use case for using Dask. So this basically goes through and calculates, this uses a volcanoes data set and demonstrates how to load that into a Dask data frame. So now we're using a Dask data frame, and when we inspect that Dask data frame, we see that there's actually no data in here because we only see the metadata. The actual data are only computed when requested. So we haven't actually, we're not loading in the actual data yet. We're creating a sort of like lazily evaluated object. We're also going to repartition the data set. So we're going to create 4 partitions so that we can basically parallelize across this whole data set within our Dask cluster. And so now we're going to create a calculation. Essentially, we're going to create a calculation for the minimum year for this data set, and we're going to visualize what that looks like. And so you can see the whole graph here is to read the data and then split it into our 4 partitions. And then across those partitions, each one is going to evaluate the minimum. And then we're going to get the minimum across those partitions in a final aggregation step. And so then I can compute that, and it won't take too long. So get negative 10,000. Okay. So the one last thing that I wanted to demonstrate is a little bit about what a gateway looks like. So this is something that not everybody would have access to because it's ESIP, which is Earth Science Information Partners. They have a QHub deployment. And so this was basically an alternative to having a local cluster. You can connect to a cluster of machines. So this basically says there's some options for configuring your Dask workers. And this is going to take a little bit of time to actually load up. So, okay, so here we have, and basically here I have the options to scale my workers, a slightly different interface than before. So now, once I've scaled up to 2 workers, you can see it auto refreshes here, and then I can create a client. Once I have a client, I can actually navigate to the dashboard for my cluster. So I can see now that I have 2 workers located on these separate IP addresses that my scheduler is connected to. And we also want to remember to shut down our cluster when we're done. So let's see, I can also scale up again. You can configure adaptive scaling. So now that I've scaled up, it refreshed again. And now if I go back here, I should see 4 workers. So this was using QHub, which is something that you can, a framework, like I said, you can use yourself. Now when I shut down and I go back here, it should be on. Okay, cool. So yeah, so that was using QHub, which is a set of software that you can stand up yourself if you have access to an AWS environment or another cloud computing, another cloud provider. Okay, cool. So that was our little intro to Dask. So let me just go down to the bottom here. Are there any questions before I go through my sort of final set of things? Any questions about Dask that I can try and answer? If you want to just post them in the tutorial prompts, I'll wait for a minute or so. I don't believe anybody can sign up for QHub, but it's something that if you have a specific science use case that you're interested in exploring, I think it's something that we could talk to. I think Rich Signell is running that particular QHub instance, and I believe they might actually want to use the credits more than they have been. So finally, just wanted to say some closing thoughts on how to learn more. So Pangeo, like I mentioned, is a totally open community for reproducible and scalable science. So this community provides documentation, develops and maintains software, and deploys computing infrastructure to make scientific research and programming easier. So I highly recommend people get involved in the Pangeo community by checking out the website and joining the community meetings. Also feel free to reach out to myself or Scott, who I know is very involved in that community as well. And then also feel welcome to join the ESO Cloud Computing Cluster. We have monthly knowledge sharing sessions, and the next one is, so this is sort of a humble plug for the next knowledge sharing session, which is Monday on a new framework called Apache Beam for geospatial data. I guess it's not totally new, but it's gaining some traction in the geospatial community. Apache Beam is another workflow orchestrator, and Alex Morose of Google is going to talk about it for geospatial data. So those are once a month on Mondays. And yeah, and you can sign up for the email list here. There's also a Slack and cloud computing cluster channel that you can join. Not that anybody needs more Slack channels, but I promise this is a good one. Yeah, and like I promised, there's also a bunch of links as per usual for learning more. So you can learn more about how to explore Landsat Collection 2 data on AWS using a Dask cluster via coil.io. There's the Pangeo tutorial gallery. NASA Oceanscapes, I'm sorry, NASA OpenScapes. They've been creating really great tutorials for cloud hackathons, so I linked to those here as well. Those are a really great resource. And so yeah, I think that's it for this tutorial. So thanks, and feel free to reach out if you have questions.